Okay, thank you very much. So, is this thing on? Can anybody hear me? Excellent. So, thanks for the introduction and thanks for giving me the opportunity to talk at this meeting. So, I'll be talking about what we have been doing to support LLVM on the IBM POWER processors. And actually, I will be modifying the topic of my talk slightly. Because of recent events, I will also be talking a little bit about what we're doing with System Z, because those are really related, at least as far as the motivation why we're doing it is concerned. So, yes, let's get started right away. I'll be talking about mostly in the first part on sort of who we are within the IBM Linux Technology Center working on toolchain and so forth, and why we are now doing LLVM, what the motivation behind this is. Then a little bit more specifically what we have been doing so far on the PowerPC side and what still needs to be done, and likewise for the System Z side. And finally, just some brief observations sort of from my point of view as someone who hasn't really any LLVM experience at all, but quite a bit of experience on the GCC and GNU tool side of things, in how it was sort of to get familiar with working on LLVM backends. As I mentioned a little bit on my background, I've been with IBM, with the Linux Technology Center for, I guess, 13 years now, doing toolchain work nearly all the time. In the GNU toolchain side, both on the compiler side, GCC backends for various platforms, and also on the debugger side, and occasionally also other parts of the toolchain. So, platform-wise, all across the spectrum, Power, mainframe System Z, the Cell, broadband engine, most recently ARM. So, but always sort of on the GCC side of things. Okay, now let's get started with sort of who are we in the IBM Linux Technology Center, what are we doing, why are we now doing LLVM? This is just sort of a general setup slide, which I'm not going in all the details, which we show everybody who's asking what is the Linux Technology Center. So we are basically the group within IBM that does sort of all the Linux-based operating system work for a variety of purposes, both making Linux itself better, adding new capabilities, enable all the IBM products, which is both hardware, software, and services to work well with Linux, and also do some special stuff with customers and prepare Linux for sort of being able to do things that it couldn't do before. In this particular area where we are working, it's really about enabling IBM server systems. Basically, for a long time now, it's been sort of really strategic for IBM to make sure that all our main enterprise server systems run Linux and run Linux well, are well supported by Linux. And this goes across the whole portfolio, starting from our System X, the Intel servers, the Power systems, where there's a variety of them from very small blade servers, small rack-mounted servers, up to the really big scalable SMP systems. And also, of course, the System Z, which is the mainframe, where there's really just two sizes, big and really big. But the idea is sort of across across the whole portfolio, we want to support Linux, providing the intrinsic capabilities that Linux has across all our family of servers, and then in addition, differentiate the various servers by the particular things that each of those servers is particularly good at. So, that's it for the marketing speech of this talk. Now, sort of, what does that mean specifically to enable Linux to run on the IBM server platforms? As I mentioned, it's one of the primary tasks that we in the LTC have is to ensure that we do have first-class support for enterprise Linux distributions, which means that sort of we care about, first of all, we care about enterprise Linux, which is sort of, not completely, but mostly you can think of the enterprise Linux distributions when you hear that term, which is right now we work very closely with two partners, which is Red Hat and SUSE, supporting their enterprise Linux distributions across that portfolio. Now there's other things that are part of Linux, some other Linux distributions that may not always be fully supported in the enterprise distros, and we don't care so much about this other stuff. But for the enterprise stuff, we really want to make sure that sort of what works on one platform actually works the same way across all the platforms. Because that's one of the big sort of selling points, one of the big pluses about Linux is that really you have this opportunity to choose your platform and have all your code work across platforms if you do it right. Now for a lot of the code that is in those enterprise distros, we don't really have a whole lot to do because it just works. Either it's just portable code, which you just recompile it and runs, or maybe if there is platform-specific code, the community already does it. But there are some components of the enterprise Linux distros where this doesn't work, where there is not enough support in the community, or where you just need special knowledge that may not be so widespread outside. And there's, of course, I mean, the most obvious ones is, of course, the Linux kernel and also the core toolchain. And there's a couple of others, but those are the big ones. And for those, we sort of consider it our responsibility to make sure that this stuff is well supported across those platforms that we care about. And from a toolchain perspective, that really means mostly Power and System Z. Because System X, everybody does the Intel toolchain. We don't really have to do a whole lot there. It just works. But Power, and even more so System Z, there's really not so big of a community outside of IBM that works on the toolchain component of things. And sort of that's, if you look back at what we did over the past, I don't know, 10, 15 years, we did contribute significantly to both the Power and System Z platform parts in GCC and across the toolchain, of course. But beyond that, we also did actually some significant contributions to common code, like the GCC auto-vectorization framework was pretty much done by IBM. We did GDB multi-architecture support, which we needed for supporting the cell broadband engine. And there's a couple of other stuff. But sort of, we usually do those things when it's particularly helpful or particularly useful to support one of our platforms especially well. Now, as I said, we did a lot of work with the GNU toolchain over the years. So I guess the question in this audience becomes, well, what about LLVM? And the answer to that is, until recently, nothing really. So, and there's two reasons for that. Really, sort of one reason is supporting a tool chain for a platform and supporting it well, so it actually generates code that really fully exploits the platform and it works well on the platform, is not a small task. It takes quite a bit of effort in developing, in testing, in doing performance work, performance analysis, all that kind of stuff. We know how much work it is because we do this thing for GCC. And in some cases, we also, within IBM, not within the LTC, but within the IBM overall, we also have our own proprietary compiler, so we already have two. Now, having another compiler was always considered, in particular by management, executive levels, and say, oh, well, a lot of work, a lot of effort. Do we want and need to commit those resources to do that? And so we were always asked, why do you want to do that? And we couldn't really give sort of the reason that management or executive level would see, okay, that's why we have to do LLVM. So far, for the enterprise platforms, there just wasn't sort of this kind of critical use cases where we said, okay, now we just need it. And basically, because of usage of LLVM has become more widespread and has become more, in some cases, into those areas where we really consider it critical, this perception has changed, and there was sort of the big shift sometime around the middle of last year, where it really became clear to us, and it became clear to management and executive level within the LTC that, okay, now we need to do something with LLVM. We do need to support LLVM across our platforms. Otherwise, we can no longer claim that all the platforms are supported equally well. And specifically, that meant for us, because again, on Intel, it works because you folks all make sure that it does. That means for us that we need to make sure that it also works on PowerPC and on System Z. So on PowerPC, fortunately, there already was a backend, but it didn't really work fully as we would have expected and needed it on our platform. And I'll go into details a little bit later. On System C, unfortunately, there was, right now, when we looked at it, no support at all. So what changed, as I said, really, what changed was the use cases. And the ones that sort of made it show up onto our radar screen are really sort of not so much use of sort of Clang as a static compiler, as a sort of straight alternative to GCC. That didn't really make the compelling use case. The use cases were really things that GCC just can't do, and that's in particular the use of LLVM as a modular component, as a JIT, and in particular in places where we said, okay, we just need it. And one place here, which is sort of surprising at the first glance if you think of it, because we're talking about the large enterprise servers, but actually we need graphic support even on those servers, because we need remote desktop support, because many applications either only have a graphical user interface, or maybe the application itself has a text-based user interface, but the installer for the application only has a graphical user interface. And that, by the way, that is the case even for some of the most important IBM applications that we like to sell. So we really do need remote desktop support. And that always used to work without problem. But now GNOME made the decision that they don't want to support the old 2D desktop anymore. They only now have the newfangled 3D desktop, which is nice, I guess. But if you don't have a 3D accelerated graphics card, there's a problem. And the problem is solved by using as fallback a software implementation. And this software implementation, because you want it to be fast, uses a JIT, and that's LLVM. So in order to support the 3D graphics, we need the LLVM pipe driver, and that obviously needs LLVM. So that's one of the reasons, and we need that for the next upcoming releases of both the major enterprise distros, because otherwise we won't have remote desktop support. But that's just one part of the picture. The other thing that was also very surprising to me when I heard that first, certain, which I can't name right now, but certain proprietary database applications actually make use of a JIT to speed up processing of SQL stored procedures by compiling the stored procedures at runtime. And what do they use as basis for the JIT? LLVM. So, and if that's not really enterprise critical, I don't know what is. And of course, there's also the use of LLVM sort of as a tool to help software development by all those sanitizer tools and by the error messages and all that kind of stuff. Again, not so much in actually using the generated code to run it, but run your source code through LLVM and those tools in order to fix bugs, detect problems, and stuff like that. And that has also been specific requirements by certain customers, which I also cannot name right now, who said, well, we'd like to move to one of your platforms, but we do this in our software development cycle, and how can we do that on your platforms? So I guess that's the story behind the motivation, why we need it. And now sort of that makes it also clear that, as I said, if we say we do support it, then it means we want it on Power and on System C. So that's why it sort of all hangs together here. But of course, technically, on the implementation side, PowerPC and System Z are quite different beasts and need completely different backends. It's a completely different processor architecture. So I'll talk about those two separately. Okay. Now, on the PowerPC side, as I said, there was stuff already there, and I guess getting back to the days when Apple still had PowerPC machines. But that's about the level of machines from that time back then that it still supports today, which is not really sort of what we want and need to get best performance on today's current high-end power systems. And also, it really didn't quite work right, and it didn't support all the features. Like, for example, it didn't support the JIT on PowerPC 64. when we were told, okay, now we need to look at the thing and get it to work, none of us had any LLVM experience. We were a bunch of experienced GCC developers, so we just said, okay, how hard can it be? And started with what you do when you start. You just run the test suite. And you notice there's dozens of failures on PowerPC at the time.
Still lots of failures in PowerPC.
Well, sort of. The way I run it, it's clean now, but
Anyway.
yes,
Yeah.
yes. And it's nice to have a good test suite and sort of getting into just running tests and seeing something fails and looking into it and seeing why does it fail or what's broken and fixing the stuff is really a good way in getting into a compiler that you don't know at all. Because you get to learn about different parts because some bug is here, some bug is there, and it's sort of interesting. And so it turned out that many of those bugs that we saw in the test suite failures actually weren't really PowerPC backend specific so much as there were a whole set of problems in the test suite itself, where the test case the test case itself just was broken on a big endian system, or on a big endian 64-bit system, or on a system where character wasn't signed by default, or all those things that that you know and love in differences between platforms. Interesting problems is also with math accuracy, like and there's sort of the test suite tries to work around that by sort of when it compares the final result being a little bit generous and accepting tolerances, but that sort of assumes that the original thing where the differences were introduced sort of show up linearly somehow in the output, which is not really true. For example, there's this one test case which is a ray tracer, which shoots rays and detects objects or not. And in some cases, the ray on Intel would hit the object, and on PowerPC, because of small rounding differences, would not hit the object, which means you get a completely different output, where tolerance doesn't help you. So that's an interesting question, and I'm not completely sure how to fix that. So I said I have a way where it runs through without problems, and that is if I run it, the LLVM output against the GCC output, set both to FP contract equals off, because the default between those two are different. But if I do that way, and then compare it, everything goes through. But I'm not able to run it against the reference output yet, because the reference output was generated in Intel, and there's tests were just different. Yep. But I guess that's a topic for maybe a side discussion. We also run into a couple of interesting bugs around the middle end, which for whatever reason just showed up on PowerPC. Like the one interesting one, which took me a while to find and then get a fix properly implemented and accepted, was where if I had a function that was doing multiple allocays with the same size, the CSE pass would optimize them into one, because why do you need two of them? And it turned out that it actually was a bug in the CSE code where it couldn't handle an instruction that had a fusrec definition and use of the same register in one instruction. It was just a case that wasn't handled for some reason. But that's all fixed now. Yeah, also one important thing what we did is we set up the build bots, which is really helpful, and it's a nice infrastructure. So we're trying to do the same for System Z, but that's a little bit of a problem because sort of we need a System C that is accessible from outside the IBM firewall, because it is being contacted by the central build bot, which is difficult for us for various reasons. But if there's a way around that, I would be very interested in. Okay, let's talk about that later. So once we got sort of the main test suite clean, the other interesting thing that we did was, well, ABI issues are always very important to get right. And GCC has a very nice mixed compiler ABI test suite where you have a large set of test cases that test all the various kernel cases of the ABI, and you can specify two different compilers, and it will build the caller with the one compiler and the callee with the other compiler, and then vice versa in all combinations, and run it in all combinations and see that it always passes. And we ran that against GCC, against current LLVM, and again ran into dozens of of problems in the places where you'd expect all the various corner cases like small structures and alignment issues and complex arguments and 120-bit integers and so forth. But interesting enough, even in some very typical types like int, where the ABI says on PPC64 an int has to be sign or zero extended according to its type to the full 64-bit register, which LLVM wouldn't do. It would do for types smaller than int, extend to 32-bit, but not int extend to 64-bit. And there's also an interesting discussion here about sort of which parts of the ABI are actually supposed to be implemented in Clang and which are supposed to be implemented in the LLVM core, which I'm not really sure I completely understand at this point, but yeah. Right now it basically works except for some very special cases, like this one I have here, where there's a GCC extension that says attribute aligned. So usually you use attribute aligned with an alignment. Let's say you say attribute aligned 4 or aligned 8 or whatever. But you can also just say attribute aligned. And GCC says, well, that means it's sort of platform specified. It should be aligned for everything that the platform needs. And both GCC and LLVM support it, but they use different values in what that means. So if it's part of an ABI, like if you have it in a structure or something where it has ABI implications. And I tried to fix it, but couldn't really make forward here because that needs to be done early in the Clang frontend, which doesn't really know anything about what the backend knows about alignment stuff. So, but just one of those issues that is still open. Now, then once we have the ABI complete, the next big test is, of course, bootstrapping the compiler, which is sort of what GCC always does, which is, maybe I just didn't find it, but at least I couldn't find any way within the Clang on LLVM make files to just do the bootstrap in one step like you can do in GCC. But obviously you can do it just manually, do stage 1 to stage 2 build to a stage 3 build, and then make sure that stage 2 and stage 3 are the same, identical, which they weren't. Not usual, and in this particular case, we didn't actually find any real code generation bugs there, but we found non-deterministic effects of code generation, where both stage 2 and stage 3 were correct, functioning correctly, but were just different because of just some random ordering decisions were made in a non-deterministic fashion, some in the PowerPC backend and some also in the middle end. But that's also fixed now, and we have Bootstrap that's good. Stage 2 and stage 3 identical. Next step we wanted to do, because we really want the JIT to work, so we need the instruction encoding to be correct. So we built everything with the integrated assembler first on. And so my naive thought was I would build the full test suite, save the object files, then build the complete test suite again with integrated assembler, again have the object files, and then they should be identical, right? And that turns out to be not the case. In fact, they were not the same because the encoding was broken for various instructions, so that was good, we fixed those. Then the code sections were identical, but still the object files not. There were differences in the data sections because of some alignment stuff that was handled differently, which is some stuff in dwarf sections and codings were actually wrong. Others weren't really wrong, just different. So we fixed that too. So right now I'm at the stage where code and data is completely identical. But of course, the object files themselves are still not identical. And that's now down to things like the order of symbols in the symbol table that the assembler writes out. And I'm not sure if that's really feasible to make identical, if that should even be a goal. But that's where we are right now.
Yeah.
You say yes, it should be?
I think so.
Okay.
I don't think it should. Yeah.
So, now, beyond those sort of just cleanup work and making sure everything works and is correct, there was a couple of things where we actually had to implement new stuff. And as usual, I'm running out of time, so I'll go over this a little bit quickly. So we did implement at least sort of limited support for the PowerPC long double data type at compile time. So, I forgot the one most important thing, of course, because the reason why we did all that is the JIT support. And sort of that didn't really work. There was JIT support for 32-bit PowerPC, but not really for 64-bit PowerPC. And also there's this thing with the old JIT and the new MC JIT. And we were told, oh, only use the new MC JIT. And so we did that. So that's implemented for 64-bit now, but not for 32-bit. So that's a little bit weird. But that seems to work too. And in particular, it works well enough to get LLVM pipe working, which is one of the things, and also this database that I mentioned. So that's looking good. Right now, I'm still working on the assembler parser, which has been a never-ending story because of various issues I ran into. But right now, all the preparatory patches are now committed, so it's all in. So it's now just sort of the main assembler parser patch itself that is currently still undergoing review, and hopefully we'll be getting in soon. And then there's a disassembler, which is still to be done. Otherwise, I think we're sort of complete as to sort of supporting all the stuff that a backend should support so that we can support all the LLVM features that it has. Except I'm missing something that... So, in the future. So far, we have really only supported stuff that we need to do to make it work correctly, to support the full feature set and make it work correctly. We haven't really spent a lot of work in making it work well, and that means supporting all the features of the current processes and getting the best performance out of it that we can. And in particular, things like VSX vector instructions is something that we would really want to be using on a Power 7, which we don't right now. And there's a lot of performance tuning that needs to be done. As Chandler said this morning, with performance numbers are always interesting. So I have a number here, take it with a grain of salt. With an industry standard benchmark that I'm not supposed to mention because we didn't follow all the rules you're supposed to follow when measuring that. That one.
We know exactly which.
So we are about 7% worse than GCC, and that is about LLVM 3.2 compared to GCC 4.7, which is not great, but it's not really, really bad either. Given that, as I said, a lot of the performance stuff just hasn't been done. So, but there's room for improvement, I guess. Okay. So far on PowerPC. Now on System Z, the situation is a little bit different because there was no System Z backend at all. But that's not quite true because there used to be one. And Anton just told me a little bit about the history, which I really didn't know about. But for a while, there was a backend in there, but then it got removed again, pretty much because it hadn't been maintained and there was no interest. So we have implemented a completely new System Z backend, which is sort of, I guess, roughly based on the old one, but at this point, I guess, used it more for inspiration than actual code sharing. We decided on sort of a particular feature set where we said, okay, right now we do 64-bit only. We only support Z10 and newer processor types, and of course only Linux. And just like what I just mentioned for PowerPC, we focus on getting the feature completeness and the correctness first, and worry about performance later. And I guess that's where we are right now. So we do have, with a patch set that I posted, and Richard posted an updated set a week ago, we do have a working C++ compiler where we basically did all the same tests I went through for the power side as well. So we're passing all the test suites, we are passing bootstrap. We can run benchmark and it works correctly in all cases. We pass the ABA compatibility test suite. Again, modulo some of those very special cases. We actually have an integrated assembler, and we even have an assembler parser, which was a little bit easier on 390 than on Power because we don't have pre-increment instructions, which is odd for the assembler. And we also have the MC JIT, and again, no support for the old JIT. So that's where we stand, and the patches are out there on the list. I'd appreciate any comments and reviews. And that's, in fact, our next step, to see what needs to be done to get it We had been hoping that it might be possible to still make the 3.3 release. Maybe, I'm not sure. If someone has tips or can help in getting this done, I would appreciate that very much. So from a technical perspective, as I said, I think it's good. The reviews we got so far weren't really anything catastrophic either, were minor things which we have been addressing so far. So we'll see. As a whole bunch of tests, in fact, Eric complained that it was too many tests, about 900 files.
What? Just had to scroll through them.
Okay, now, but once this is in, of course, it's not done. Again, we did no performance optimization at all, and you see it in this, using the same benchmark numbers as with PowerPC. We're about twice, so 15% worse than GCC, which is significant. But again, no performance optimization whatsoever. And if I compare that to where we were on GCC, when we had the very first implementation that just worked correctly, and then spent the next couple of years optimizing it, we get 50% improvement. So I don't know if we can get 50% here. It's unlikely because we're starting from a higher base. But I think we can do something about those 15%. And that's where it gets interesting in sort of working with the more special things, like to get something that works correctly, you don't have to exploit all the weird instructions that the platform has, as long as you do the standard thing. But if you want to get optimum performance out, you really have to make use of everything your platform provides. And that's where, in our experience with GCC, that's where you run into limitations of sort of the framework. And we haven't met that point yet, but maybe we will when we go down that road. And that's going to be interesting to see. And of course, all the usual things like instruction support for the current processors, instruction scheduling, tuning, all that kind of stuff. And maybe at some point, 31-bit support. It's not 32, it's 31-bit because mainframe is special. You know, it's the reason why 31-bit is because the 1-bit tells you it's not the 24-bit support. You know, this is an architecture that goes back to the 1960s, and code from the 1960s still runs, so.
Hey, the support in GCC just fell out, so of course it will just fall out there, out of the I-30. Right.
Yeah. And just sort of, it's 31-bit pointers. The data elements are still 32-bit, so. Of course. But that means that a load address does a 31-bit add, so you can't use it for regular add, because that would be 32. So interesting things. Anyway, I think I'm pretty much out of time, but just a couple of small observations. As I said, I'm pretty new to LLVM, so if I'm saying something that it might very well be that I just missed something obvious and I just didn't know about it. But sort of my sort of high-level stuff, when I started working with that and looked into it, it looks pretty similar. I mean, it's a compiler. It does the same things. It has parsers that are about the same as corresponding parsers in GCC. It has, well, GCC has these weird MD files, which are processed by various tools and generate code. Well, LLVM has the TD files that are processed by various tools and generate code. So sort of familiar on the backend side. Of course, in the when looking into details, of course, there are differences. So LLVM does obviously seem to be a little bit more, or actually a lot more flexible in what it allows the target to do in sort of adding stuff that isn't anticipated by common code, right? So you have a lot more flexibility in just adding completely new passes and just putting them in the pass manager and it works. And that's something that's really, we have tried to do that in GCC for a while, but I think we're not quite there yet. So what the target in GCC does is really, it can parameterize passes that exist in the middle end, but you can't just do something completely new. And that's certainly nice. And of course, also the sort of the layering is much more clean. With the most obvious thing that you see is that in LLVM, you just build all your targets, and they're all built together into one executable. And you can't do that in GCC, which is another goal that we've had for years or decades, but it's just very hard to get there from where we are in GCC. So that's looking nice. On the other hand, of course, if you have a complex thing, there's always things that you run into that may be confusing just because you don't know them, or maybe they're confusing because they just don't work right. Like I mentioned the pre-inc instructions. And just recently their discussion in John Grossbeck had been very, very helpful in helping me figure that out. Yeah, one other thing is with encoding bugs, when trying to track down encoding bugs, I got really confused by sort of, you have your instruction where you put your operands in, and then in the encoder, you refer to those instructions. And interestingly enough, you can either refer to your operands by name, or it will just use them by number, the first, the second, and the third, which is really confusing if you're trying to refer to them by name, but misspell one. In which case it will fall back to, well, that one must have then be meant by number. and that's the type of things where really you have to sort of read the generated code and read the table gen code and try to find out what's going on. Which I hadn't have to do that particular thing for GCC. And one part of that, which I think explains some of those things, is that actually LLVM does really have nice, good documentation for the higher parts of the stack. The IR and so forth is really nicely documented, much nicer, I think, than GCC with the Gimple stuff. But if you look at the backend side, there's actually GCC has quite good documentation for the RTL stuff and the backend passes and what that all means. It's really all spelled out in sort of a reference documentation section. On the LLVM side, there is documentation, but it's sort of more like a tutorial, like look at what Spark does and do it the same. But if you have something that's not just like what Spark does, maybe I just didn't find it, but there doesn't seem to be any sort of reference documentation of what actually what's everything that you can write in your TD file and what does it all mean.
Change too fast. About the only way we could make it more helpful is just to delete the Spark package.
Anyway, I think I'm out of time. I have a little bit, but that's what I said already, sort of just looking at the backend parsers, it all looks very similar, except for the added flexibility in being able to add stuff. And also just sort of some example, again, how the files look similar. But of course, you see the differences in basically how you define your instructions so that the compiler knows what it means. Am I completely out of time? I think yes. Yeah. So let's just skip that. Summary, I already said that, so let's just go right away to the questions.
Yep, so we have short time for questions as well. Any questions?
Did you have any observations on the quality of the test suite itself, coming from a GCC background?
Well, I liked the idea of sort of using a whole suite of full applications and use them as test suite, which is nice, which GCC doesn't really have. As I said, there's issues with, obviously, if you use full applications, then the applications may not be fully portable, so you can run into issues in the test suite. But in general, I like the test suite.
So you think it's good enough when you're porting to a new target? It's good enough. Use a test suite. You will find 99% of the bugs.
You find a lot of bugs, yes. If you find all of them, you never know.
Okay, don't need the mic. Have you got C++ 11 atomics yet? And if so, did you have to do anything for power memory order?
The mic is for the recording. The recording.
I'll get that. Sorry, I should
Repeat the question, apparently. Have you got to C++ 11 atomics yet? And if so, did you have to do anything for PowerPC's weak memory order?
Okay, so we haven't looked at that specifically, so from a front-end perspective. So what we did is, both in Power and on 390, is we did implement sort of the backend atomics. So those are implemented, and then they seem to be working. Whether that will give you the C++ 11 stuff automatically, I don't know. We haven't looked into that.
So there are some atomics in the Clang itself or in the test suites. So if you can compile and run them,
Yes.
then they probably work mostly.
Yes. So both of the LLVM and Clang tests would run without bugs.
Last question.
The atomic stuff in the test suite is a good baseline, but you really do need to look at this. The interesting thing is that it's very easy to implement the atomic built-ins in a conservatively correct manner, and it's extremely difficult to implement them in a truly efficient manner on a weak memory architecture machine like Power.
Yes.
And so there's a great deal of interesting work there that will be of particular performance impact in highly concurrent applications.
Okay, good point. Thanks for. As I said, we'll focus on correctness first, performance later, but very good point. Thank you.
Last one.
So actually just a comment rather than a question. When you get to the correctness, we actually have someone in our theory group has published a paper proving the correct instruction sequences for Power for each of the C++11 memory model operations. So I can give you a pointer to that.
Excellent, thank you.
Well, thank you.
Thank you very much.